Today we will have videos first of all in the beginning itself on the use of prefabricated vertical drains, and we will take up some examples also. I will just show you this particular video in which you can see that this is actually prefabricated vertical drain I was just mentioning in the last class. We have a sand drain in the olden days and we have now a PVD. Actually the design is not very different, but the rate of construction of this is very fast, like 10 meters it can go in a few minutes time. You can see here that it is actually a real time operation. You can see that it is going very fast, then it has reached the required depth of installation, say maybe 10 meters or something, then it will be cut, that is it. You can see lot of other drains here along this line. Say for example, this is a installation of drains line along which it is there. Yeah, now it is cut. So, this is another one which will give some idea. Right. You have an embankment here, you can see that they are very close. Like these are all say for example, this could be the heavy embankment of 5 to 10 meters and not about 5 meters, you can say that, and you can see it once again like a series of prefabricated verticals are done or installed actually in the field. This is that once it is done, you have actually, you can see a drainage layer also here, then you have this embankment maybe about 4 to 5 meters. So, in the last lecture, that was the lecture 10, we studied the preliminaries of pre-compression. This approach has resulted in a number of techniques involving accelerated consolidation of soils. People started with sand drains, and the vertical consolidation as well as radial consolidation was taken advantage of, and subsequently they went to prefabricated vertical drains, because as I just mentioned in the last class, there are some problems associated with the installation of sand drains. Number one, the availability of material itself like sand. The second thing is that the way it can be done, the speed of construction could be much higher if you see the prefabricated vertical drains. You saw it in the video that it can be very good, and in many places in wherever soft soils exist, you have this prefabricated vertical drains installed all over the places to take care of the loads that are imposed. Okay. Then we will also see vacuum consolidation, which is something again like we are supposed to construct 4 to 5 meters of embankment, but there is a possibility that okay, if you need to construct that much of height, it is okay, but somewhat a preload can be reduced even using vacuum. You will see its advantages of vacuum consolidation also. There is another method which is called high vacuum densification method, which has come just about for the past 2 years. Chinese have discovered that, and that they find it is very effective compared to many of the other methods also. So, as I just mentioned, the advantage of the preloading is that, or preloading or any of these techniques is that we try to accelerate the process of consolidation into a very short time, say maybe less than a year, to see that the subsequent settlements are going to be minimal. Like this is the final settlement for the design load. You see that to reach that settlement level, this consolidation in a regular manner takes very long time, maybe the time could be about years maybe 4 5 years, but with this you are able to preempt the whole consolidation, and then see that even if there is a release also, it is all right. The settlement is less than I mean you are able to achieve that settlement in a shorter time. That is an example what we want. So, as I just mentioned, I gave an example last class, where you had some sort of surcharge, which is because of the preload. In fact, this 115, no, you assume that there is a permanent load that can come because of the extra load, that 115 kilonewton per meter cube. This numbers can be calculated using, you have a number of theories or elastic solutions, where you know the load, whether it is a uniformly distributed load or point load or even a triangular load. Triangular load represents the loading because of the embankment. The loads are there, and one can calculate what is the extra stress that you get from the particular loading. So, at some point, say for example, you have 10 meters of the embankment, you will be able to calculate stresses at every 1 meter level. What is the extra stress because of the embankment construction of 5 meters? It could be very high, but as you just go down, the additional stress that you can expect from the load is less, or it could like, that is what we say sometimes, twice the breadth, like pressure bulb, all those concepts we know. And what we say is that essentially we would like to see that this loading is taken care, and then for in this case the depth, this is a simple illustrative example, one should do very systematically, and there are some programs available and all that. So, the average effective overburden pressure at the middle of the clay layer is 210 kilonewton per meter cube, and then the thickness of the clay layer is 10 meters, and the compression index is 0.81, initial void ratio is 2.87, and the CV consolidation coefficient of vertical consolidation is 1.08 meter square per month. So, we are trying to discuss in terms of months, because okay, you have to just convert what you get in the laboratory value, you get normally in seconds or minutes, you make it to months, because we are more comfortable with construction times. So, we will try to calculate what is the total primary consolidation settlement without pre-compression, and how much is the surcharge you need to apply. We have seen this in the last class, and it is about 415 mm is the consolidation settlement that you can expect, and that with the figures like this, with the principle that we have studied last class, we can calculate that knowing the degree of consolidation in the mid plane potential and time factor and all that, you can just calculate that the degree of consolidation is you can get, and say for example, the preload that you have to apply, in fact we assume some level of 6 months or 9 months time, like as I just demonstrated last class, that within 9 months you must be able to complete this consolidation. So, how much of load I have to apply, that one can calculate, and this is, you can see in this example, that is a 287 kilonewton per meter square, which is a big number. And how do you do that? As I just showed you a couple of slides last time, where you can put sandbags or any of the material, and you can, this say for example, you assume a bulk density of 20 kilonewton per meter cube and 5 meter high. If you just stack everything, it gives a preload of about 100 kilonewton per meter square, and the required surcharge is very high. So, what we do is that you better try to reduce this required number, and you may have only this. So, sometimes maybe 10 to 20, it is very difficult. So, your objective is to reduce this preload, and that is best achieved by using the sand drains or PVDs, we will see. And say for example, I try to redo the example with sand drains. Assume that the radius of the sand drain is about 0.1 meters or 10 centimeters radius or 20 centimeters diameter, and the effective diameter, as I just mentioned last time, that there is some area of influence around which it acts as a drainage layer. Okay. So, you have a sand drain, and there is some area around which it can be very effectively considered as a drainage layer. Now, instead of like early it was essentially a clay, but because of this it tries to draw all the water particles towards the drain, and then there is a release of pore pressure both at the top and bottom if it is a double drainage conditions, and there is a dissipation of pore pressure. So, this D is about 3 meters is an example. We assume that vertical consolidation is equal to radial consolidation also, this is another assumption we are making, and as I just mentioned, it could be actually horizontal permeability could be much higher than the vertical permeability because of the layering and all that. So, and then I also just mentioned that because of the use of the sand drains or whatever, there is a zone next to the sand and the clay where the permeability is low and the layer is not very effective, that problem is there. There is a, so that we say that it is a smear zone, and in this case for this illustration we assume that there is no smear. In fact, the PVDs have the advantage that there is a very less smear compared to sand drains. So, we saw that the same example, the settlement was about 415 mm, and this is a typical patterns that we have seen in the video also. It could be triangular, it could be square, and as I just mentioned, there is some radius over which it can be very effective as a drain, and we call it, it is an axisymmetric problem, and we have this for the same calculation. We will just see that you have this expression from the basic consolidation theory, right, and so like we are trying to calculate UV, the point, this TV is already obtained earlier, and what you are trying to do is that we are trying to calculate the number of sand drains here. Okay. So, DE I assumed as 3 meters, and then the radius of the sand drain is about 0.1, and you will get a number 15. Okay. So, once you get this 15, and this is actually vertical consolidation number by knowing its time period, and so there is some, as I just mentioned, sand drains enhance radial consolidation. So, we have some equations as I just mentioned, and the relevant equations which relate the degree of consolidation to spacing of drains for no smear case are as follows. Actually, there are two types of loading, one is called ramp loading, the other one is instantaneous loading. In the sense, loading can be applied suddenly, and then but ramp loading, like you sequentially slowly construct one by one, just it is like a ramp, like maybe 10 kPa, 10, 15 kPa, 20 kPa, 40 kPa, 50 kPa, 60 kPa. So, that is a load that you can have. So, one can really, that is the case, and you have some lot of people have worked on this particular problem on consolidation theory. In fact, in 1930s, 1940s, there is all these equations have been derived long back, were derived, and they are quite useful, and they have an expression called M, and M is actually, it gives the spacing of it is related to the spacing of sand drains, and even it can be even sand wicks also, like PVDs. Okay. So, this is a radial consolidation, that degree of radial consolidation. You can see that this particular thing involves two terms A, the term A which is nothing but it is related to M, M again is related to N, and then you have TR which is nothing but the time period, time factor for radial consolidation. So, you have again this is a time factor for radial consolidation. So, you have these numbers, Tc is the construction time and D is the effective diameter. This is a simple example here. So, the Tr is nothing but CVR T2 by D square, and as I just mentioned, we would like to see the consolidation within 9 months time, right, 9 months time, that is what the objective is, and D is 3 meters, is a radial, right, it is radial, so 0.27. So, actually one can develop tables or equations. So, people have a tendency in the olden days, what people were trying to, you have a say you may have a simple software, then you can feed in all the numbers and you will get, actually the objective is to get this degree of consolidation because of vertical consolidation as well as radial consolidation. This is actually the objective. Okay. So, this is when this is objective, one can use now ready made software, but in the olden days people had tables, like if I n equal to 10, 15, 20, 30, what should be the values of TR. They were, if you just go back to the previous slide, you have this UR and all that. So, essentially from these sort of expressions one can get the UR, and once you get the UR and also the UV which we already got. So, for example, this is 67% and 58% is what we already achieved. So, essentially 86%, and now what is the preload that you have to get for this? Again we have to go to the figures that we considered earlier, and for this effective stress increase and also the degree of consolidation, you will get a factor 0.22. Actually, in the previous case it was much higher, it is only the preload. Now, you can see that actually 115 is the load that the additional stress. So, you will get about 25 kPa, it is much less, you got about 287 kPa roughly, if you remember 287 is the number required, but because of this because of the sand drains of this particular size and diameter, it got reduced to 25.3 kilonewton per meter square, which is a big difference. Like you do not need to go for higher preload, you may just have some sort of say for example, this could be if you take a bulk density as 20, right. So, it could be hardly maybe 1.5 meters or something, 1 meter or something like that, is it not. So, what I meant was that this is something that one can take advantage of it, and the concepts are another important point that we had to calculate here is that you should be able to calculate degrees of consolidation at different times after installation, because we are claiming that, or we are we know that this consolidation like it can be very low, and then we would like to increase the consolidation using the sand drains or prefabricated vertical drains. For the same example, I will just little not the same, but a similar typical example. I will just give you that the radius is about 0.1, DE is effective diameter is 1.8, you can see that it is little different, and I take CV equal to CVR, and a ramp load of 96 kilonewton per meter square is applied over a period of 60 days. Like I slowly apply the load, so that actually what happens, you in a soft soil area, you should not allow the things to happen, collapse should not occur. Like if you suddenly apply the load, there is a shear failure, and then you can't use the area, it is something very bad, like totally collapses. So, it will not take any load. So, that is not a requirement here, that is a dangerous situation in fact. So, what we do is that we apply a ramp load slowly, we call it ramp load, and then we apply a ramp load of 96 kilonewton meter square per over a period of 60 days. So, in this case we go through the same examples, I will show you N equal to dE by RW. So, this again number is 9, and see actually there is we calculate here what is the time factor for 60 days we have applied, and then the double drainage and these are coefficients. TC is 0.086, this factor which is corresponding to full load, which is ramp load is at the top of the ramp load, like once you complete that loading, it is about 60 as I just mentioned. So, for one, see the thing is, it is okay for 60 days, it is fine, but you must be able to calculate every month. Our objective is what is the degree of consolidation 1 month, 2 months, 3 months, 6 months, like that. So, TV equal to CV T2 by H square, like CV, this is 30 days, 30 we will keep it here, and so you get some factor here. So, for the TC is known and also TV is known. So, and then like I will show you this figure, this is what I was just mentioning, that the ramp loading actually, okay, like excess pressure that we have applied on the soil. Okay. So, now this is called the degree of consolidation, and then this is a time factor. So, the numbers in the circles are the construction time factors, like as I just mentioned, you have time construction like in the previous example, previous slide, these are the two factors. Then we are looking at what is the degree of consolidation, it is about 6, okay, it is about somewhere here, like if you look at those numbers, it is quite low, it will be somewhere here, because it is 1 month only, you are looking at only 1 month, not long time. So, one can really calculate based on different time intervals. Okay. Once you know that, I will show you some more information, and from again this is another expression that we have for 60 days, okay, one can get, and again from this degree of one can use the equation as well. So, you will get all these terms, and then for no smear case you will again have this sort of expressions, area is given, and the for next day it will be 9.7% instead of 6%, okay. Like that it could be like one can increase, and then one can again use this equation, and then finally it becomes 15.1, and the settlement that you have after this this time, is about, say for example, in this same, you can use the same expression and then you will get about 0.54 mm. So, like that, one can calculate some of these numbers in a comfortable manner every month, and then just see that. So, this is how like this is what we want to have with time versus settlement is what we would like to have with the PVD now. And the as I just mentioned, PVDs are much more comfortable to use because of the ease of fabrication, quality control, economy, and sample disturbance to soil is very less during installation. This is another important point that one should realize, and like the difference is that we had an equivalent diameter there, and now since the shape of the sand drain is something more of a rectangle, the flow pattern around the drain is considerably altered from the cylindrical case. So, you have to calculate the equivalent radius. So, as I just mentioned, these are some examples of the PVDs. So, you can calculate the effective diameter like we like with the 2 into this sort of expression, and also then once you know this dE, you can also calculate the effective drain influence area. There is another expression depending on the pattern. Okay. So, once you have those patterns, you can go ahead with the design and then complete the process. The design is similar, but the advantage is that they are much more scientific. So, the trial embankments are something that are quite useful as I just mentioned, and they are quite there are some of the like normally people do this because it helps in avoiding the sample disturbances and uncertainties in the sampling and field properties. This we have discussed. I will just show you some small example what we studied. As I just mentioned, when the consolidation times are just about 9 months to 1 year, one can use coir drains. I just showed you a couple of drains in the last class, where you have number of drains, one made of jute, one coir and all that. So, this in association with Coir Board of Government of India, I just took some material where you have a drainage as well as filter done, and these are all the properties that actually these are also given here. What is its tensile strength, what is its it's a fiber plus sisal material, coir fiber, and the thickness, what is the thickness, what is the tensile properties like 338, whatever is given, it's everything is given. So, I was trying to compare their flow properties with conventional PVDs that I showed you yesterday, like white color one, and you can see that the flow rate per unit width we try to measure, and normally, and then these are all somewhat compressive materials, like if you just apply some load, there is a compression that occurs, and higher is the compression, lower is the flow. So, one can see that, one can get it, and this can be for different hydraulic gradients. One can get I equal to 1.5 for the same sample 1, I just showed sample 1. So, you have relationships like this, and you have these two are sample, one is for the coir actually, these are all, they are all for the coir, and then these are all for the white PVD. There are 3 types PVDs I showed you. So, you can see that the whatever the thing is the sample PVDs, for example, these are all dotted lines, this 1, 2, 3, there are dotted lines a little higher, in fact. The permeability or the flow properties are here for different compressive stresses. Compressive stress in the field, what is happening, there is a that is called compressive stress, right. There is some you put a drain, but there is some load acting on it, which we say like K naught times sigma V or whatever. So, you are trying to look at those thing also, because you want a full flow properties established. Okay. So, at full depth also there should be a flow, like there should be. So, we try to verify, you can see that in fact coir drains are really doing well. Okay. So, this is in fact one important point one should know, and this is another example that same thing, like under different hydraulic gradients, how are they performing. Like you can see that all the samples are a little higher than what it is, but whatever they have comparable properties. That is one important thing, is that when you see the variation of hydraulic gradient with flow rate per unit width, like unit width you should take for different compressive stresses for coir PVD and synthetic PVD. You can see that the things are quite reasonable, is it not? So, the advantage would be that one can use where the these materials are abundantly available, people should encourage some of the efforts. Of course, both have their own advantages. you can see that example that I was just mentioning for a typical embankment that was constructed. I mean that we can take a typical example of 5 meters and all that. You can see, you know, for a period of 1 month without coir geotextile or coir drain, you can see that this the consolidation is about 27% after 1 year. Now, as I just mentioned, radial consolidation equal to vertical consolidation, and if I just see that this is the line. But whereas as I just mentioned, the vertical consolidation will be slightly smaller. So, you put that, I mean radial, and so you see radial consolidation is higher than the vertical consolidation, normally 2 to 3 times one can measure, you know, in the field. So, you can see that 100% is achieved within maybe 4-5 months, which is a very nice result actually, with some of the actually coir properties are they are applicable to both materials. It is very interesting observation that yes, some of these materials could be used and you can get what you want. This is an important observation. So, as I just mentioned, we will see how it can be installed, like of course, you saw the video, and we should have a very good modern equipment. In fact, you know, the so for example, some companies there, you know, they must have good approved equipment which causes a minimum disturbance of the subsoil during installation operation, because disturbance leads to reduction permeability, that is again an issue. And the first step in the installation is to prepare a working surface for the installation rig, like you are bringing a big rig there, and working surface must be level and have enough bearing capacity so that the installation rig can operate. In fact, you may not believe there are cases where the installation rig can sink in. If the soil is so poor, definitely you can't bring in. So, you may have to create a temporary platform for it. I will just show you some more diagrams on this. You may have to create a working platform for the crane to stand and then, you know, execute the work with some sort of arrangement. So, typically this working surface is also a part of the gravel drainage layer. As you just saw, the drainage layer is at the top, and if this working surface can be a part of the drainage layer, it is nice because it is comfortable. After the site is stripped, a geogrid is often placed to support, and then drainage and working layer is placed. Actually, sometimes it is always, you know, you saw that coir drains were standing and all that, and you try to put cover the sand and then put a geotextile layer, you know, which can work as a drainage layer, because sometimes you know, sand is of course a good drainage layer, but sometimes they say geogrid could be placed. In fact, it can even take care of the uneven settlements. Say for example, you are trying to put some crane is coming later, some sort of all these rigs are coming. So, if you want to that bearing capacity, if it has to increase, you can really calculate what is the bearing capacity that you need, and you can provide a geogrid. Okay. So, some sort of geogrid one can place to see that there is no problem with this case. Okay. Now, so you have some of the equipment like, you know, mandrel, we have seen that it can go up to long depths, and it can be a triangular pattern, and see there are different types of drilling actually, like we will just see that, and a suitable rig will operate ahead of the PVD installation to prepare holes through the hard upper layers. Okay. Once the wick drains are placed above the drainage layer, you know, a drainage layer is placed on top to you know, in preventing, like, you know, you need to connect all of them, and the drainage layer is typically a free draining layer or a drainage geosynthetic material. The drainage layer needs to be so sloped that the water will flow away from the foundation area, like that is very important. The slope needs to take into account any planned settlement, so that the water flow is maintained throughout the consolidation phase of the project. So, how do we install it? There are some typical methods, like it can be you know, displacement methods, like it can displace the soil. Of course, the soil is so soft, it can be displaced nicely, and the particular methods you have driving vibrations, and pull down using a static force, right, washing, like, you know, you can, so combinations of the above. There are different types. You can drive, you know, you can use vibrate. There are a couple of issues. A mandrel with or without a disposal show is used in each case, like, you know, I saw in one of the showed you in any of the earlier photos where you have a simple show, and then it reaches the required depth, and see the thing is that it will be like this. once you want to remove it, it opens up like that. So, it stays there. So, that is a very interesting thing that you put it, and when you tries to withdraw, then it opens up, it forms a shoe just bottom at the wherever is the required depth, and then once you know that, then you try to pull it back, it will not come, right, because it is there is some force that is preventing it. So, once you realize that, you cut it and then you are operating everything through the computer that for example, as I just showed you, they are all highly sophisticated ways of handling things, and people take them to the required depth and then cut it, right, up to the appropriate margin, so that it is not too out of the drainage layer also, like it should not project too much out of the drainage layer, right. So, one can use drilling methods, of course, depends on the type of soil, and then standard, all could be used. Okay. These are all many methods one can have, and washing methods one can have. These are all they are there, like similar to stone columns and all these methods. These types of methods are there in the field, but we should realize and check what type of methods are suitable. Of course, the contractor normally he knows exactly what should be used, and he has his own way of handling, and the project cost sometimes depends on that, even the cost of the I mean whole project, as well as the efficiency of installation, everything depends on the methods that we are using. That is very important. Like in fact, see the installation from a barge, you can see that the mandrels are being from here, the soil is so soft in some places, like you may have to take them on a barge, okay, like it is possible. So, one should be very careful, and this is one another typical example, like you are trying to use PVDs for you are constructing some slope here, extra slope here. So, this is actually what happened, one should have, see what happens, water comes here, then that should not create a shear failure here. So, all the water should go through this prefabricated vertical drains, that is how these drains are installed here. This is another application here, this is not a consolidation type, but the application here is that PVDs in fact have been used behind the retaining walls also to increase the rate of drainage. Here this is another typical example where you try to have two slopes, but within the two slopes the possibility is if the rain comes, this material is good and this material is good, but at the interface there is a possibility of weaker layer formation, and the water should not enter, and then finally the new soil that you have placed should not come out. So, what we do is that we try to design properly and see that all this is taken care of by proper drainage arrangement, like at the bottom, at the top all the water should go into these things, and then at the bottom you should have a collecting mechanism, right, like similar to in fact there is a in Vijayawada there is an RE wall which is constructed about 30 meters high. It was like this. Of course, they did not have PVDs, but they have drainage material of made of aggregates. Okay. This is another one that one can have, the top one can connect and all that. So, I just want to give a small example. This I have taken from one of the suppliers or installers of the geosynthetic products. This is a case study for improving the bearing capacity using a PVD for one coal and iron ore stackyard. Actually, this is from one, I do not know, you must be familiar with some of these projects, like it is a place in Newport in Gangavaram in 15 kilometers south of Visakhapatnam, and the objective is that they are trying to have coal stacks of coal stack about 12 meters high, iron stacks of 10 meters and something like that. So, you can see that coal stack and iron stack. So, the objective is that soil is so poor here that it needs accelerated consolidation, and this is the plan of the whole area. And like, so I mean the way they did was that they had design parameters to ascertain that you have 8 number of boreholes were made, and you can see stratification, in fact a dredged sand which exists at our top layers, marine clay 1 to 3 meters, soft soil 7 to 15 meters, below again N value I think reasonably okay. So, the available bearing capacity was about 3 ton per meter square, which was less than the required value required. Okay. So, what are the properties? You can see that liquid limit is in the range of 21 to 102, sand it is more of silty to clay material, and plastic limit is in the initial void ratios are 0.62 to 2.2. Compression index is given 0.38 to 0.92, coefficient of consolidation values are given, cohesion values are given, friction angles are given. So, essentially lot of information is available, and so they have done it. So, they did the PVDs 10 to 18 meters below the ground level, original ground level they have taken. Spacing is about triangular pattern, and they have, so consolidation period about 65, depending on the spacing. Actually for 1 meter spacing they have 65 days, for 1.5 meter spacing 175 days. Okay. Thickness of the sand mat about 300 mm, like what I said, drainage layer. Then horizontal drainage system, geotextile pipes filled with boulders. As I showed you in the previous slide, one can have geotextile pipes filled with boulders as gravels. PVD laid, it was laid horizontal, some PVDs they can be laid horizontally, as I just showed you in the previous slides. And machinery was used as hydraulic stitches. So, you can see here also that it is all horizontally done also. So, this is some example. Then sometimes some time the contractors also expected to show that yes, their system works. So, post treatment and assessment and analysis is a very important project that they have done. So, in fact, they have used piezometers, cassette grinder type we have 5 numbers, then vibrating wire 14 numbers, they have settlement recorders plate type 13 numbers, magnetic 7 numbers. Readings were every 4 days, that they are taking every 4 days when the loading started, and later after that 7 days, like as I said during the initial process they could be little the 4 days, and later it was 7 days. So, they have sections here, like you can see that this is that piezometer. So, their objective is to find out excess pore pressure and settlement. Okay. So, they have in fact in theory, in literature if you look at it, because people are always looking at these issues, and the degree of consolidation, how you have to have, say you may observe some pattern in the field, but you also should try to develop some theoretical models to understand them. In fact, they used a 2 method called Ashoka method and hyperbolic method. Actually here the difference actually in the Ashoka method, the settlement at equal time intervals is measured, plots between the present settlement and the previous one are plotted, and the intercept of this like they have they will have a slope actually of 1, this actually you will see that if you have 100 settlement S minus 1 and the current settlement, they just try to plot this line here. Okay. They also based on this and some more analysis, they would like to get the settlement S100 for ultimate settlement. There is one way. There is another method which using the hyperbolic method. In fact, hyperbola is a standard constitutive model in basic mechanics, which is actually we call it Duncan-Chang model. What we do here is that we calculate the graph of time versus settlement we plot, and so actually whatever is that curved form, it becomes a straight line in the, if you plot time versus settlement plot, and graph in the form of a hyperbola is then the inverse of this slope of the parabola. So, this hyperbola is converted into suitable coordinates, and one can calculate ultimate settlement. Okay. The settlement long settlements long term settlements one can calculate, and these are all typical observations they had for pore pressures. Okay. Pore pressure variations and all that, they had some understanding of this. Then settlements also are measured, and then you can see that the observed settlements are there. Then there is a 2 methods, they have tried to obtain what understand what these 2 methods give, and what this found was that, I mean actually this some of the case studies they have, they are only their things are only specific to that particular problem, and also their ability to interpret the data available. So, what this observed was that the plate settlement recorders are more reliable than the magnetic settlement recorders for marine clays. With the application of the load, the pore pressure increased and dropped down slowly with time. The pore pressure variation indicated about 50 to 60% dissipation degree of consolidation. Hyperbolic method is they are more comfortable with hyperbolic method, and so it, since it is much more close to values that you obtain, like you have a pore pressure, I mean you have a equation for using the hyperbola to measure settlement, predict settlements and the pore pressures, that seem to be reasonably okay compared to Ashoka method. But as I just mentioned, these are all some specific thing, case to case basis. And another important point that I would like to indicate here is that there is another technique called vacuum consolidation. Vacuum consolidation is something again people have proposed in 1952, like you create a vacuum in the lab, like the advantage of the vacuum is that you try to remove all the air present, I mean like if you want to reduce even in soils, there is a saturated soil, and if you just create a vacuum, there is a drainage that takes place, you have an accelerated drainage that takes place. So, they were using it in some applications like landslides, but then what prompted people to use this vacuum consolidation was that the conventional surcharging was little costly, because the cost of placing and removing the surcharge fills, you have to place the surcharge and remove the surcharge, and difficulties they were there, that was one thing that they had. And there was also people did not perfect how to maintain the vacuum properly. But then with the situation now is somewhat different, that the direct and indirect costs of placing and removing surcharge with the advantage of sealing landfills and impervious membranes of landfills. Actually vacuum technology has also improved. What we have to do is that you will see that the vacuum technology has improved, and also the possibility of the cost of the fill that you have to place for surcharge was also very expensive. So, actually this people have to use geomembranes in landfills, and you have to create some vacuum, also use some sort of vacuum technology for sealing. Actually you can see with the advent of technology for sealing landfills with impervious membranes for landfill gas extraction systems. So, the technology has improved so much that it has become little more economical or viable as a replacement or supplement for surcharge fill. You will see that how it is. So, it is an effective means of consolidating or accelerating the improvement of saturated soft soils, and the soil site is covered with an airtight membrane, totally thing has to be completely covered with an airtight membrane, and a vacuum is created underneath it by using a Venturian dual Venturian vacuum pump. There is a system of pumping system here. The technology can provide an equivalent preloading of 4.5 meters high, which is as compared to conventional surcharging fill. So, the advantage here you can see clearly that you have to go for instead of going for 4.5 meters of sandbags or whatever surcharge, if you apply properly this vacuum, one can get a very good effect. Okay. So, what happens here? Why is it effective? So, what it does is, instead of increasing the effective stress in the soil mass by increasing the total stress, like what we do is that you keep on loading and allowing it to consolidate. Here in the vacuum assisted consolidation preloads, the effective stress, the pore pressure is reduced while maintaining the constant effective stress. Actually constant total stress is same, but you start removing water, the effective stress increases. That is what the effective stress can be increased when applied with the combination of surcharge fill. Field experience indicates that a substantial cost and time savings by this technology compared to conventional surcharging. Of course, these are all in the many places outside, and you can see that here this is an example. This is the area to be consolidated, and these are all the sand drains, and you can see that you have a geomembrane here, which is laid, like you have done everything, all the process is clear, like this is a dewatering, this is a drainage layer, this is a fill, okay, and whatever fill, you are going in lifts actually 1 meter or something like that. So, what we do here is that we are creating the vertical vacuum, there is the vacuum pipes. Okay. So, yeah, they are all connected, and then because of the, so this is a vacuum air water pump, vacuum gas phase booster. So, there is some more additional arrangement. In fact, you are trying to increase the effective stress in the fill also. Increase the effective stress means if you put air, like we know that if there is an air into the soil system, effective stress increases, the total, actually earlier it is only the pore pressure in a saturated soil, but if I have air pressure which is called suction or negative pressure, the effective stress increases, it will be much stronger, like similar to a saturated soil and unsaturated soil. Unsaturated soil will be much stronger and less compressible compared to this thing. Okay. So, you can see that this you have a system here also, you are trying to consolidate this portion also by a suitable arrangement, by arrangement like this. The principle is that, like we are all familiar with the PQ diagram, P is nothing but sigma 1 plus 2 sigma 3 by 3, Q is sigma 1 minus sigma 3, and soil, actually this is a line which is called K naught line. K naught line means which is along this line K naught conditions prevail, which means that there is no horizontal strain, right. The air pressure is at rest, So, what we do normally, now you start loading actually in the field. So, what by process of surcharge placement, what are you doing? We are trying to, because the rate of loading is faster than it can consolidate, you can see that the P value, P will come down, this is the effective, actually P dash is a mean effective stress, P dash here, it is here, then it will come down a bit up to B, there is small difference, and so that is why you have to control both. Why is it happening? That is because there is a pore pressure increase, because the soil is poor, like consolidation rate is not very effective. So, what happens if you really start loading faster, the rate of loading will be very faster, then it may even reach the failure line, which is nothing but our which you get from C plus sigma tan phi or whatever, right. Like you can plot the Mohs circles, you can get this, you can get from that line, right. For the effective stress analysis, you can get KF line, you can also get K naught line from the consolidation theory, thing, and so this is actually, if you try to increase the rate of loading, what happens, this may lead to failure, which we do not want. So, what we do is that why we need monitoring in the field, what do we monitor? What do you monitor? It is actually the pore pressures we monitor. See that the pore pressure is not really leading to higher, Q will increase, but at the same time Q should not lead to failure. So, we do not want this point to reach here. So, that is the reason why we are measuring effective stresses and pore pressures in the field. So, the advantage of in the regular surcharge consolidation, that what we do, so we apply lot of stress, right, and so that this is what preloading is done, so that it moves away from the failure line, that is fine, that is what we do. That is actually, you can see that there are always some horizontal strains there, because the moment the soil is the soil state, we call it, it is in this range, then there is always some horizontal deformations that exist, but if the horizontal deformation is too much, then the total collapse takes place, right. If the horizontal deformation should not be too high, because it is a combination of shear and volumetric strains, and it should not lead to failure. So, you can see that this is a region at which horizontal strains are higher, and this is a region along which horizontal strains are 0, and here what is happening? you have created a vacuum, which means that you have increased the effective stress. So, P has increased to a particular point and the still the it is not strained, there is no strain there, they always like say that the compacted sample will have a less compressibility compared to a saturated soil, as simple as that. So, you can see that here, because of the vacuum at the same effective see the same effective stress you applied vacuum, and it resulted in it results in this QP plot, it is like this, but you will get the effective stress is increased, right, because that UA component you have to add. So, for example, pore pressure pore pressure is generated like the you say sigma dash equal to total stress minus pore pressure minus this plus, actually this becomes additional. So, the effective stress will increase because it is it's a opposite of, it is a suction, it creates a suction. So, in the process the total effective stress is increased, the effective stress equal to total stress minus pore pressure plus suction. So, that is what it is, and some constant whatever, so that is what exactly we are doing. It is isotropic type of the pressure is isotropic, like you are withdrawing the pressure from all the 3 directions or applying pressure in all the 3 directions, what I meant. You can see some more I can have a clear idea on this. Vertical stress profiles, like in situ soil conditions, what do? You can see that this is a total stress, total vertical stress. How do you get? Gamma B into depth, like up to say 5 meters, 10 meters, 15 meters, 20 meters, I will get this effective stress. You can see, say for example, at 5 meters depth, the effective stress is about 100 meters, which means like say 5 into 20 is 100, like 10 into, so like 10 into 20 is 200. So, it is like this, okay. This is called the total effective stress. Then you have also measured pore pressures, right. So, if you measure pore pressures, this is the line, and so this is the effective stress region, right. So, this is one what we say. So, you can always measure this. Normally what do you measure? You measure only total pore pressures, total stresses, right, in the field. How do you measure pore pressure? It is like water column raise, gamma W into height, okay. If there is a water pressure raising, water pressure is nothing but the pore pressure, excess pore pressure, right. If you put some next to a soil and there is a pore pressure, like there is undrained situation and there is always a pore pressure, excess pore pressure in relation to atmosphere, you just measure that and then measure that it is in terms of the column of water, like if it raises by 3 meters or 2 meters into its gamma into means 10 kilonewton per meter cube is approximately the effective stress. So, this is in situ conditions. Now, what did you do because of the consolidation or the surcharge, conventional surcharge? You have increased the total vertical stress, okay. The pore pressure line is here. So, you have increased this range of effective stresses, that is what we did, and you can see that it starts from 0, pore pressure is 0, right, and then it increases. Now, with vacuum assisted surcharge, you can go up to minus 1, 1 bar. 1 bar is a pressure that you can apply. So, minus 100 kPa. So, this is the region and this is that. So, you can clearly see that you have increased the effective stresses, effective stress in the sense that you are able to create an effective stress field less using this suction, that is what it means. So, what we are trying to see here is that the current main application of the vacuum assisted consolidations include replacement of standard preloading techniques, like okay, as I said, standard preloading test means adding lot of sandbags and other this thing, and because the problem is, as I just mentioned, it eliminates the risk of preloading induced foundation failures, like you try to stack in all the preload that in one place, but it could lead to failure. So, what should be done? You try to combine the vacuum consolidation preloading with both, you can have both of them in some sort of scarce fill areas are going to be where there is a scarcity of fill, scarce actually. The method has been used to build large development projects on thick compressible soil. The combining VCP with surcharge preloading to increase foundation stability and thereby optimize preloading stage sequence and reduce project time. In fact, you can even optimize on the construction process itself. The application of vacuum, once your sealing systems and everything is perfect, vacuum systems, it just takes 2 days or something like, just to stabilize. You have to apply vacuum. Exactly what you are doing is you are applying vacuum, and people have been doing lot of field studies here. So, in China, then in France and ESA and Bangkok and many places, they have verified the effectiveness of the vacuum assisted consolidation in conjunction with vertical drains for site improvement. Cost estimates based on these projects indicate a significant potential for cost savings over conventional surcharge fill preloading for an equivalent height of 4.5 meters height. So, there are a lot of advantages, and I will take up a few more points on this, and also I will talk about a few more issues on the ground improvement using dewatering techniques. Thank you.